Good morning, everybody, and welcome to day 2 of the technical session here at Java 1. My name's Tim Ellison. I'm going to be talking about Java and real-world compatibility. Now, they've kind of given us a really big room, and I have some charts that have some pretty small font examples on. So if you sat at the back, you might want to move forward a bit so you can see all the details that we put up on the screen. And if you were here earlier for the sound check, you'll have heard Foster. That's the highlight of the talk already, right? So I can't beat that. Thank you for the entertaining start. The mandatory disclaimers from IBM. So let me just introduce myself briefly. I have history of implementing virtual machines from Smalltalk through to Java and other kind of stuff. I'm currently based at IBM UK in Hursley, which is about an hour's drive outside of London. And that's the center of the Java Technology Center for IBM. So I look after all the class library. I look after Java 8 deliveries. Obviously, sometime next year we'll be looking to do that. And I have an email address that looks like that. Okay, so what we're going to talk about today is compatibility and why Java compatibility is important to everyone. Right? Users and implementers alike. I'm going to describe the different types of compatibility that we consider, and then talk about why those different types of compatibility are important, what you can do to protect yourself from changes that are made in the Java platform, and then at the end there just give a little indication of some of the tools that are available to help you address compatibility in your own code, as well as finding things in JDK itself. So this is a little kind of scene setter about why compatibility is important. Obviously, Java SE is offered as a universal computing platform, which means that we all get to program in Java and leverage the implementations of Java across a wide variety of different types of systems. And at IBM, we're shipping on Windows boxes, on Linux boxes, on big mainframes, on embedded devices, and so on and so forth. So you get the benefit of the broad ecosystem where Java is implemented, and of course all the surrounding ecosystem of books and technical conferences and all that kind of stuff, right? So I'm assuming that everybody is pretty on board with that idea, given that we're all sat here at Java 1. So the Java SE implementation itself is specification-based. And by that I mean there are a number of specifications which describe how Java behaves. They're embodied in specs like the Java language spec, the VM spec, platform API spec, of course, the Java doc that everybody's used to reading as an implementer. And these are very detailed documents. They describe to people like myself as an implementer how we need to implement the code so that we fulfill our contract to people who are writing applications as users. And of course, the same documents are read by users to understand what sort of assurances and guarantees they're given by implementers in terms of how their programs are going to behave. Now, Java evolves over a period of time, obviously going up through many different major and minor revisions. And as Java evolves, the specs evolve with it to describe the new types of behavior. Because we have the specifications, we can collaborate on what that sort of behavior should be. And so we actively collaborate as a Java community of implementers on specifications. And yet we compete on different areas which are not part of the specification, such as performance, memory footprint, diagnosability of problems, and so on and so forth, and platform coverage. And those are areas where we can compete, but within the bounds of the specification. Does that make sense? So the compatibility promise that you get with Java is that when you stick to the rules, your program can be written once and can run anywhere, right? And I put that in inverted commas. And so when you're a programmer, you're programming to the Java platform. You're not programming to any one particular implementation. When you write your code, you're not writing it specifically for a Linux box. You're not specifically writing it for a 31-bit Z-series mainframe machine. You're writing it to the Java specification, the Java platform. And then you get that war of promise. The implementer's job is to take the specifications and kind of minimize the distance, the conceptual distance between what the specifications are requiring me to provide as an implementer and the underlying capabilities of the platform. So I want to really exploit the underlying capabilities of the machine platform, but do that in a way which is consistent with the assurances which we are giving to our Java programming users through the specifications. And because we have those strong specifications, different people can make different trade-offs in how they do those implementations, right? So at IBM, we kind of cover the gamut, but I'm obviously making different decisions about when I'm going to JIT compile the code and how much memory I'm going to use for large WebSphere installations that are running on mainframe devices or clusters of high-end server machines, compared to other people who are making decisions about how Java is implemented on a constrained embedded device. And so you get this very broad ecosystem of implementations, and with different goals in mind of what they're trying to achieve as an implementation. And that in itself can give rise to some compatibility issues, which we'll take a look at a bit later on. Now, the way that you can ensure that once you have written your implementation, that it does conform to the Java specification is through the Technology Compatibility Kit, the TCKs. When applied to the JREs, they're called JCKs. So you may see those terms, they're kind of one and the same thing for the purposes of this discussion. This is a suite of tests that you're obliged to run and pass in all different modes before you can declare your implementation to be Java. And that is the assurance that when we talk about the Java platform and we put the coffee cup logo on it, people understand the suite of implementation specifications that implementation has passed. Excuse me. So in the green box down there at the bottom, this is lifted from the Java language spec. I'm sure you can read it if the font's large enough. But the key point here is that all the sort of implementation details apart, the intention is that a program written in the Java programming language should compute the same result, should have the same effect across all different machines implementations that have. Okay, so let's try and drag this back to the real world a little bit. In the real world, of course, compatibility extends beyond those specifications. And we see many applications which have a dependency beyond that which is written down. For example, the specification doesn't say what the list of system properties will contain, right? There's a definition of sort of a minimum set of what it must contain, but the system properties can extend beyond that minimal set, and some applications may go looking for system properties which are not part of the specification and will appear on implementation but may not appear on others. Command line options. Again, anybody that's sort of moved around between different versions of Java will be quite familiar with the fact that different implementations have got different command line options. There are some which are standardized and are well understood. Obviously, minus class path is one which you're going to see everywhere. But the minus X options, things which control the garbage collector, things which control the JIT implementation, these are not standard. These are ones which, if your application requires modification of the runtime behavior of the JRE, you'll be specifying some of these command line options, and these could well trip you up when you go to move between implementations. And also building dependencies on other things which are not part of the spec. So I think messages which are put out by the VM, whether they are the dash version string that goes out there. I've seen applications which are parsing that. That's not even kind of closely standardized within different releases of IBM Java. So we kind of get caught out sometimes breaking people who are putting dependencies on our own implementation details, never mind things which are part of the Java specification or not. So when we talk about compatibility, it's these two different things, right? It's the write once, run anywhere promise that says that the code that you write for the Java platform is going to work everywhere. And you can have that promise for sure. You can get WARA in real-world Java as long as you constrain yourself to the set of promises which are made by the specification itself. But I'm going to use compatibility in a slightly broader sense than that. And that is that not only within an individual version of Java and trying to get it to run across different implementations, but across different versions of Java, there are compatibility issues as well. And as you want to move up through different versions of Java, obviously to get bug fixes and enhancements and that sort of thing, and get the advantages of security fixes. As you move up through Java, as we'll see in some of these later examples, there will be some compatibility issues you may have to deal with. As a platform implementer, Java collaborators through specification have to make these balances and trade-offs between what is the right thing to do and what is the least disruptive thing to do. So let's go and have a look at some examples of those things. And I'm going to break down my examples into 3 different areas. And I'm calling them functional compatibility, meaning when my program is running, does it have the same effect as it had last time it ran? Source compatibility, if I have some Java source code and I recompile it, does the result have the same effect as the last time I compiled it? And binary compatibility, which is, can I take 2 sets of class files and still combine them together even when one set has changed, right, and still have the same effect at the end of it? Okay, so let's delve into a bit more detail on each of those. Functional compatibility in Java is, as I say here, primarily defined by the Java specifications. The specifications themselves are very carefully considered. The information which is written into the standard, which you'll read in Java docs if you're an API sort of level programmer, are there as your assurance of behavior, but we also deliberately do not put things into the Java doc where we do not want to make such assurances. And that could be for a couple of reasons. Either we would expect or we know that the libraries behave differently on different implementations in that aspect. Okay? Now, often that is called out in the spec to say there is implementation detail here. But sometimes it isn't. Sometimes it's left quiet. And if you're not given the explicit assurance in the Java doc, then you shouldn't sort of run your program to see what happens and then make that as an assumption. That's the way it's going to be on every implementation. And the other reason why it might be left out is because the we want the ability to change the implementation and produce further optimizations. And so, again, if you specify precisely how an operation is achieved in that API, that could very well limit your ability to change the implementation later. And having those implementations could lead to some breakage. So a couple of examples here of things which are not specified. Hash maps iteration order. I think there was in Brian's core libraries discussion yesterday evening at the BOF. There was a discussion about the changes which are being made to Java util hash map to allow for better hashing of strings to avoid collisions. The hash map itself has an iterator, of course, which can iterate over the values, but the order in which those values have been inserted into the map, into the hash map, is an implementation detail, rather than the order in which they're stored. You put them in your sort of application level order, they are stored based on a hashing algorithm, and when you iterate over the results, the values of the hash map, they come back in an unspecified order. Now, as an application writer, if you, through experience, write your program, see which order these things are coming out, and assume it's always going to be that way, you will be broken. And as I say, a concrete example, which was discussed yesterday, was the changes of string keys in hash maps will be changing in Java 8. Also seen examples of things like walking the stack. You can get hold of the stack from Java. but looking back up the stack to see where you were called from, the stack trace is not a specified format, and that's definitely an implementation detail which will change. Parsing messages, which I spoke about earlier, things like version string and so on, right? Error messages, looking for those. They're not part of the specification. The Java platform is very good about ensuring that when you are given a promise in the Java doc about some type of functional behavior, that promise will be maintained over a version to version release of Java. When it's found that the implementation is out of sync with the specification, as sometimes happens, we have two options, right? We can either change the implementation to actually do what the spec required it to do, or we can change the spec to actually fit what the implementation is doing. And that's one of those judgment calls I spoke about earlier, right? It depends. It depends on where we are in the overall life cycle of that particular Java release. If it's new code that's just been written, it could be seen as just a straight bug that it's not doing what the spec required it to do, and in those circumstances, the right choice will be to go in there and change the implementation. But if the code has been out for a long period of time, if people have been coding to that particular type of implementation, you could actually do a lot more harm than good to change the implementation to match the spec. And in those circumstances, the right thing to do really is to go and update the spec and say, well, actually, this is how it really happens. Just to show that this is not particularly uncommon, this is a grab of, and it's not the whole list, and I don't expect you to be able to read the details here, of course, but these are just a whole bunch of changes, of functional changes, which have happened in the Java platform between 5 and 6, I believe. So let's look at a simple example. And again, I apologize if you can't read that chart too good. I'll try and call out some of the salient points. So I've got a snippet of JavaDoc from the JavaLang float class. And the particular method here is parseFloat. So in Java 6 API spec, the relevant part is that it says that it's going to parse a float from a string. It could throw a number format exception, and it will return the float value represented by the string. So I have a little snippet of code just below the line, which says I've got a public class called parser. Doesn't do much really. It's just going to parse a float, and I'm passing in null. Okay, so you may expect to get a number format exception, but in fact what you get is a null pointer exception. Now the spec didn't say that this method could throw a null pointer exception. It said it would produce a number format exception. And so here we have the implementation behaving differently to the spec. And so in that particular case, in Java 7, the spec was updated. Right? That had been out there. It seemed like a reasonable thing that passing null would produce a null pointer exception. And so if you go and have a look at the Java doc for the same method in Java 7, you'll see that the spec has been updated, even for something as fundamental as lang float, to say that it will throw a null pointer exception. And so the same piece of code there written passing null on Java 7 just behaves the same way, right? It still throws a null pointer exception. And the point here is that, when we talk about compatibility, it's not just in how the code behaves and how the implementation behaves, but it's how the specifications are written, right? You can break compatibility by changing a Java.com comment like this, for sure. Here's another example. This one was taken from NIO Channel's datagram channel. In this case, the specification has been changed to say that if the socket channel is not bound, so here the methods send, receive, and connect were changed when invoked on an unbound socket. So you've created a new instance of data channel, and you've gone to do a send and receive on it directly without doing any bind. In the previous implementation, in Java 6, these methods used to just return null because you hadn't done the prerequisite, which was to bind it. But that wasn't specified. In Java 7, when you go to do one of those operations, it'll do a default thing, which is to do the bind first, and then continue with the operation. And the spec, again, has been enhanced here to say that that is what will happen. So this is another case where this is a change both to the implementation and to the specification. So the specification used to be quiet on the subject, and the behavior was that you would just get a null back in this particular circumstance. Now the specification is explicit and says that a bind will be performed, and the behavior has been changed to do the bind and continue with the operation. Now that's obviously quite a significant change in both aspects, and on retrospect, in retrospect, doing the default bind there was the right design choice, and that's why it's written that way in Java 7. However, it could also be argued that that was quite a fundamental change to the behavior of this, and there may well be, rightly or wrongly, applications who fall foul of this particular change in the specification of behavior. And so in this particular case, there's a system property introduced. And you'll see this in a couple of places where you can specify -d sun.nio.ch.bug level and set it to 1.4, 1.5, or 1.6, and that will revert the behavior of data channel in this particular case, but potentially other areas of the class library code as well, to the earlier type of behavior. So here's an instance where the compatibility has been broken. The functional behavior of the application is changed because the platform has changed its implementation. And yet, to preserve compatibility, the system property has been introduced and given people the ability to revert back to the previous implementation. And it's not just things which are quite as obvious as that, right? So you could find those by looking at Javadoc. But there are other things which you may not find quite so easily. I've given a couple of examples here. In Java 5, the class file format was changed so that now when you have references to classes in your code, they will be class literals in the class file. And that's important because if you have code written like this, if foo is an instance of your class, right? Prior to Java 5, that would cause a class load for the your class definition. But beyond Java 5, it doesn't, right? It's just doing a test against the literal name of that class. And why does that matter? Well, because when the class is loaded, the class will run its class initializer. And that class initializer could have some side effects. And those side effects could do things. So, this, again, it's a change that's in the VM spec. It's not one that necessarily people would go hunting for and find, and yet it could have quite a significant change in the functional behavior of your application. In this particular case, those references and the class files that are generated are done by the Java-C compiler. So it's even more interesting, really, in that that functional change occurs if you recompile your code and run it on those VMs, not just by running the previously compiled code on a later VM. You may well see some functional changes due to changes in the way we optimize the code. So again, as an implementer, we do just-in-time compilation of the bytecodes and execute those. So the JIT is at liberty within the definition of the Java memory model to rearrange some code within the bounds of the read and write barriers defined by the specifications. And unless you're very careful, well, I say unless you're very careful, there are some circumstances in which it is possible that your functional behavior changes because the JIT has rearranged some of those bytecodes, again, within the assurances given by the Java memory model. If you're not familiar with the Java memory model, you may get caught out and start doing crazy stuff. And then we also see some functional changes and behavioral changes due to the way which different people have implemented the specification, all the way down to, the particular example I have here is class.getName. And we spent quite a long time in IBM tracing down a bug that was caused by class getName on Oracle's implementation and returning an interned string. So you always go back to the same instance of string for a particular class name. And then it was used in an identity hash map later. And in the IBM's implementation of the VM, we didn't intern the string, we returned a new instance of a string. So of course the identity hash map wasn't matching these things. The spec doesn't require it to intern the string, and so somebody sort of further down the track had made that assumption. Likewise for locking and so on, you can soon get into interesting situations. So just to summarize on functional compatibility, we assure that we're compatible across the Java platforms using the TCKs. You should stick to the specifications and the assurances that specifications give you for how the platform is going to behave. And when things break, then I typically will be either changing the implementation or changing the spec or providing some sort of get out of jail command line options to allow you to switch between those two things. When do functional compatibility changes get introduced? Well, really only at major platform boundaries, right? And even then, only after very careful consideration. So it is taken very seriously by everybody. They are quite hard to spot because it could be changes in implementation. You saw the list of RFEs I put up earlier. Each release comes with a list of compatibility changes that are made for function. So it's worth sort of seeking that out and taking a look at it. And when you need to resolve these functional compatibility differences, it really does require some sort of understanding of what the intent of the program was to ensure that the new function and the new behavior is satisfactory, or you need to change the implementation to match the new behavior. Okay, so let's move on to source compatibility. So when I talk about source compatibility, what I mean is, given a sort of .java file that contains Java source code, does that result in the same set of binaries when you compile it using your new Java platform, your different Java platform? And the most obvious sort of case to consider is that you get a compile time error, which may occur because some of the changes to the Java language have made your previously valid program invalid. Or it may be even the other way around, right? You may have had a program which wasn't valid in one version of the Java language, and it suddenly becomes valid, which is probably a less interesting case because not many people sort of keep around invalid programs and try them on later versions. So it's more interesting, obviously, the case where you had a program which used to work and compile successfully, and now it no longer does. So the main requirement here for source compatibility is, if I compile my source code, does it resolve all of the references that I have down into the platform to the same, the same in inverted commas, the same references in the platform as it used to do? Well, why wouldn't that happen? Maybe the language has changed to introduce new keywords, and it could also happen because we've introduced new types into the platform. So let's take a look at a couple of examples here. So again, if you take a squint at the top little snippet of code, this is a change that for programs that used to work on Java 142. So here I've compiled this program on 142 and run it, and it produces the output, the word false. However, when I try to compile the same source code on Java 5 onwards, I get compile time errors. And that's because one of my variables is called assert, and assert became a keyword in Java 5. And so it doesn't make sense as the Java assert keyword to appear there. And my program, which used to work perfectly well on 142, trying to recompile it on Java 5, it doesn't compile anymore. here's a different example. So again, little snippet. Here I've called out just printing the result of testing whether this class, which is called parse.class for historical reasons, is a proxy. So proxy.is proxy class. On 142, the answer is false. It's not a proxy class. But when I come to recompile this on Java 5, exactly the same source code, it fails to compile. And the reason here is that because if you look at the import statements, I'm not explicitly importing the specific proxy that I'm talking about. And a proxy class was introduced into the Java net. So we're talking about two different types of proxy here. We've got the object proxy, and we've got the network proxy. And so because I've got Java Lang reflect star and Java net star, it suddenly becomes ambiguous in Java 5 when that second proxy was introduced. Which one are we talking about? It wasn't ambiguous in 142. There only was one thing called proxy in 142. Come Java 5, there are two things called proxy, so the compiler can't resolve that and throws up an error. So this is a change in the Java platform itself. And I'm using the Java platform as examples, but of course, all of these examples could equally apply to your application code. And that's why it's kind of sort of discouraged to use the star notation for importing everything, because it can lead to this sort of ambiguity, and it's better to explicitly import types. Here's a different type, a little bit more subtle, I guess, of source incompatibility. I guess it's more kind of behavioral and source together. So here in my little program, I'm creating a new instance of big decimal representing the integer value 1. So that's just a digit 1 on that constructor. And the matched constructor here is big decimal double, right? Because that's the closest match that the compiler is going to find. Using the Java language rules, I can widen the int to a double. And so that is a perfectly valid program. There is no explicit int constructor, and it will match the double and do what you expect. However, in Java 5, an explicit int parameterized constructor was added to big decimal. And so now, when I compile the same program, because there is a more specific version which explicitly matches the int, I'm no longer linking my source code. When I compile it, that's no longer a reference to the method, which is the double constructor. It's now a reference to the int constructor. Now, in this particular case, I believe it doesn't really matter. We're still constructing a big decimal. The impact of moving from that double-based to int-based constructor is not going to be an issue for us. But again, it kind of demonstrates that as you evolve your class libraries and as the platform evolves and you're recompiling your code, the same piece of source code could end up actually referencing different things inside the target application.
That was actually an issue for my company.
For whom?
For my company.
Okay, so I was just pointing out that was an issue for somebody.
Well, we started having builds fail for certain applications.
Right. For this particular case of
The big decimal, yeah.
big decimal, okay. And especially, when those constructors will likewise have a side effect, that's really going to be noticeable. Okay, so source compatibility. The goal is that update releases for Java will be maintaining source compatibility. Again, if it's a major release of Java, if you're going from 5 to 6, 6 to 7, and 7 to 8 onwards, there will be some work required to move up between these different versions. It's not necessarily a write once, run anywhere story here. The Java platform may well break source compatibility if there is enough justification and reason to do so. So, it's just to flag it up, really, just to let you know that these things are possible. And you need to look out for them and do the adequate amount of testing and so on. Not only at the API level, and that's the place where sort of true consideration is given to source and functional compatibility. But when you start reaching into areas of the platform which are beyond the spec, then pretty much all bets are off. So any references from your application to COM/SUN packages, you have no assurances that that stuff's going to continue working. In fact, almost the opposite, right? The COM/SUN packages and equivalent things which are not defined by the specification, their role in life is to support the APIs themselves. And as I mentioned in the early part of the talk, if we think of better ways of implementing some of those APIs, we reserve the right to change the implementation potentially quite substantially, and those internal classes may well behave differently, they may well disappear. Especially when you look out towards modularity, where there's a potential there to start to scope some of the visibility. I mean, often the reason you can reach those things is that they're marked as public, and that's so that API types can reach over into their implementation packages to reference a type. But of course, it unfortunately means that applications can also reach into those public types. When we get modularity, we'll be able to have a module level scoping, which means that you won't be able to reach from the application down onto those implementation types at all. So that, again, could cause some sort of breakage. Solving these sorts of problems, well, some of it can be done from this sort of mechanical transformation. Obviously that assert that I showed in the early example is a case where you can look through your code, figure out any places where you have assert. It's a variable name. You have some discretion as to what you call that. So that could be mechanically changed. And let's look at binary compatibility. So binary compatibility is interesting because the assurances that we're looking for with binary compatibility is given two sets of class files, can I link these things together without getting a linkage exception? That's pretty much binary compatibility definition. So it's a pretty simple definition. And what does that mean in terms of the assurances that you're looking for in your binary program files? Well, perhaps you are a provider of APIs, right? You have a set of libraries of reusable function which you're distributing either in-house or out to folks. Or you have dependencies on other third-party libraries, and you want to ensure that new versions of those programs are binary compatible and replaceable units with later versions. And of course, you want to do that because not many people are writing applications that are completely standalone where you compile all the source code. We're often linking to binary libraries ourselves. So as library implementers and library providers, library users, we need to understand what binary compatibility means for APIs that we're going to consume or provide in binary format. By the same token, as a Java implementer, we need to understand what the rules are that allow us to evolve those class libraries. So one way we can ensure compatibility is to never change the signature of the methods and types and things which we are providing. However, that can be very limiting. And so there are a set of rules which allow you to change the binary signatures of your classes whilst maintaining binary compatibility, which of course means it will link in with existing programs in the same way I did previously. Each Java version's goal is to be binary compatible with earlier versions. One aspect of this is just getting the file to load in the first place, right? So when you run your Java program against a particular class file, pretty much the first thing the VM is going to do is check the version number of the class file and check that it's versioned in a format which it can understand. So here I'm just running my little Java test. I compiled it on a later version of Java and tried to run it on an earlier version of Java, and the VM is throwing this exception saying it's an unsupported class version error, which is pretty straightforward. What does that mean? Well, there is a magic number embedded in the header of the class file, which describes the file format version. And just for your reference, here are the sort of version numbers which are accepted by different versions of Java, and you can see that everybody accepts version 45.0 onwards, and there's a pattern for life beyond Java 1.1. So version 1.n of Java will be version 45 to 44 plus whatever the n number is. So for example, 1.6 can understand version 45.0 to 50.0 class file formats. However, just because you're running on an older version of the JRE doesn't mean that you have to stick with the old version of the compiler. In fact, to the contrary, encourage people to move up to the latest version of the Java source compiler to get all of the fixes in the compiler and the optimizations in the source compiler itself. And you can use the -target flag to say, generate class file formats which will be understood by this earlier version of the VM. Now, of course you can't use any APIs which are in the later version, so you also would have to specify the boot class path of the Java C tool itself so that it compiles it against the appropriate class libraries. But use later versions of the Java C compiler even when you're running against early versions of the JDK. So that's one place in which you'll see binary class file incompatibilities is the version numbering. Other places that we've seen it are things like bytecode optimizers, obfuscators, injectors, that sort of thing, which go in there and they meddle around with the bytecodes and the ordering of it and so on. Some of them are perhaps not as careful as they should be and may well produce class files which are not compliant with the class file format specification. And again, you'll get verify errors, or linking errors. So I wanted to just do a quick sort of dump on the screen here of how you would be able to evolve class APIs and maintain binary compatibility. Again, this is not an exhaustive list. It's there to show really that there are lots of different ways in which, as a library developer, we can evolve Java and maintain binary compatibility. And likewise, as a library provider, you can do likewise. There's a URL there. There's quite a good paper on the eclipse.org website. Of course, all this is in the specification, but there's quite a good summary that's written on the eclipse.org website, which outlines a lot of these rules and says which ones are compatible and which are not. And the one that's probably worth calling out here, really, is in the list of things which break binary compatibility is adding public or protected methods to an interface. And again, if you were at Brian's talk yesterday in Lambdas, he spoke about the virtual extension methods that are coming in for Java 8, which will sort of remove this particular restriction to the extent that it's introducing a default implementation. So this is sort of seeing that there is a binary breaking change and working around it and saying, how do we get around this particular constraint? And this particular case is it's going to be very helpful for evolving the existing Java class file, maintaining its binary compatibility and ensuring that you don't get those linkage errors. So I did kind of look pretty hard to see if I could find some of these in the platform, and there's a good job. There's hardly any to choose from. So this is a kind of a very modest example, really. And it's down in the bowels of some AWT code, Path2D double, where a particular API method was changed from not being final to being final between 6 and 7, which is a binary breaking change if someone were to be subclassing that. So you would have been, in the past, been able to subclass that particular method in Java 6. In Java 7, you wouldn't. But again, I think this is one where the right judgment call was made. Because who is going to subclass that thing is sort of not designed to be subclassed, and that's why it's marked as final. So now it will fail to link if you have done that. The other place of sort of binary level compatibility I wanted to touch on was serialization. Now, serialization is obviously very useful when you're transporting objects across some sort of a protocol like RMI, or some protocol used by RMI, I guess. The binary representation of the object contains a serial version UID, which embodies as a hash the definition of the class at the point at which that object was, that instance of the class was serialized, which is all well and good. However, if you have a class which is serializable and you serialize it and you persist that particular object, you now have to be very careful about how you evolve that particular type definition to ensure that you maintain binary compatibility of the serialized form. And the serialized form UID, as I say, it's a hash that embodies a whole bunch of internal methods as well as all the public and private methods and the field definitions and the orders and so on and so forth. So it's pretty tight and going to be pretty difficult to evolve the class in a way which doesn't modify any of those things. You're pretty much limited to changing the body of methods. So, again, the URL there that shows you precisely what the UID is based upon. And I think the general rule that's pretty much accepted for serialization now is that if you do have a serializable type, it's to hard code the serial version UID. So the serialization framework will look for an instance, a static variable called serial version UID for a particular type as it's being serialized. And if it exists, it will put that on the stream. If it doesn't exist, it will compute it. So if you hard code it, then you pretty much have control now over the definition of compatibility, because you can change that UID when you introduce a breaking change for the serialized form. And if you don't change, if you're not breaking, if you're able to deserialize using the same form, then you don't need to change that number. So, kind of final thoughts here. As an API producer, obviously we have to think very hard and long about the implications of changes and what they make to the different areas of compatibility, whether it's functional source or binary compatibility. As an API consumer, there are steps that you can take to ensure that your exposure to those changes is minimized. I've spoken a little bit about the API docs. Again, compiler warnings are your friend in this instance. If you see things which the compiler's flagging up, telling you not to do something, investigate it, figure out what it's talking about and why that is the case. Another good way of doing it, of course, is to get early access to development builds. And OpenJDK is a place where you can show up, you can have the discussion about compatibility, you can also get early access to builds and try your program. If you see breaking changes in the platform, flag it up. Again, it may well be something which the developers have deliberately decided to do, and a side effect, it may be something which hasn't been seen before. The place to have that discussion is OpenJDK. And I just want to kind of end with a little plug. The WebSphere Application Server Migration Toolkit is a toolkit which IBM provides as a free download. This embodies all the different rules that I've spoken about here, plus others. Now, it's called the WebSphere Migration Toolkit, and it's kind of targeted towards people moving App Server. But in fact, part of that is moving the Java SE version as well. So whilst it is possible to go and sort of look at the compatibility document that's produced on each Java release and see which ones apply to you, this particular tool will rummage over your source code and flag up places, potentially with quick fixes for how to resolve some of those, but it'll highlight places where there have been some compatibility changes and you're using those APIs or those types, and give you a chance to find them and resolve them. There's some final links for various tools and IBM places. And I end with a copyright statement. That's all I have. Thank you very much for your attention.